The coordinate plane that you're familiar with is called the rectangular or Cartesian coordinate plane. And when we plot values on a Cartesian coordinate plane, we plot them with two numbers, an x-coordinate and a y-coordinate. The x-coordinate is our horizontal movement and our y-coordinate is the vertical movement. With those two numbers, you can describe any location on the Cartesian coordinate plane. But now we're looking at the polar plane. And here we don't refer to our locations as a horizontal and vertical component like we did. We refer to them by a distance from the origin, which we'll call r, think of it like a radius, and then a particular angle of rotation, theta. So if I have an angle, and then how far that point is away from the origin, we can describe our points that way. And so we have three example problems for plotting points on the coordinate plane. In the first one, we're going to plot an r, a radius of 3, and an angle of rotation of 30 degrees. You can see our polar plane is going to look a little bit different. So if I have a point with an r of 3 and a theta of 30 degrees, we know that this right here, this is 30 degrees of rotation. That would be our theta. And so for this one, we're going to go 3 units away from the origin and 30 degrees off of our polar axis. So this point right here is 330. I'm going to graph my second point in green. Now we're going to do or, but then this says negative 45 degrees. Remember, for our basic trig, that if I have a positive angle, we go counterclockwise, and a negative angle goes clockwise. So 45 degrees, you know, if this would be negative 90, we know that negative 45 is going to be right there. That would be our angle. So what we're going to do here is we're just going to do 45 degrees and 4 units away from the origin. So a radius of 4 and then an angle of rotation of negative 45 degrees. Our last point that I'm going to plot in red, we can use our angle of rotation in radians. So now we're going to do 2 pi over 3. If you're not familiar with what that is, that's going to be 120 degrees. But then a negative radius. Let's see what that looks like. So 120 degrees would be right there. That would be our theta right there. Now, the only thing that's going to change with that negative radius is that instead of going 5 units this way, we're going to go 5 units this way. So 1, 2, 3, 4, 5. That point right there is going to be negative 5, comma, 2 pi over 3. So that's how to plot points on the polar plane. On this slide, we're going to see if we start with these polar coordinates in the form of r theta, can we convert them to a traditional Cartesian or rectangular point of x comma y? And if we plot this point on our polar plane, I think it will become evident how to do that. So if we graph our point 8 comma 60, so we're going to do 60 degrees of rotation and 8 units from the center. There's our r and our theta. Now what we're doing in this case is we care less about the r and the theta, and what I'm wanting to know is I'm wanting to know what is x and what is y. And with some basic right triangle trig, we can do that, because what I've created, if I drop this vertical right here down to our axis, is we've created a right triangle. So what I'm going to say is I'm going to say that the sine of a 60-degree angle equals opposite over hypotenuse. And if we multiply both sides by 8, we see that our y-coordinate is going to be 8 times the sine of 60. If you do with special right triangles, this one could totally be done with a special right triangle as well. And our y-coordinate would end up being about 6.9. To find the x-coordinate, to find our horizontal component, we can keep using our right triangle trig. So now I'm just going to say that the cosine of a 60-degree angle is equal to adjacent over hypotenuse. And then I'm going to solve by multiplying by 8 on both sides. And x is going to be 4 even. So our ordered pair here is going to be 4, comma, 6.9. Now let's do one more example, and hopefully by seeing 2, you're going to recognize the pattern and be able to generalize. So let me erase my graph over here. For problem number 2, I'm going to change this to 45 degrees. And so what we see is if I plot this point, it's going to be right here. So 6. We're looking for that x and that y. And then we've got 45 degrees right there. Well, if you're good with special right triangles, you may already know the answer to this, but we're just going to solve it using standard right triangle trig. And so what I see is that the sine of 45 equals opposite over hypotenuse. And then I'll go ahead and show the cosine. The cosine of 45 to find our x-coordinate is going to be equal to x, the adjacent over the hypotenuse. So this is going to become 6 times the sine of 45 whenever we solve it. And this is going to be 6 times the cosine of 45. And we see that both my x and my y are going to be about 4.24. So that's going to be 4.24, and this is going to be 4.24. So in order to convert this to a rectangular coordinate, it's going to be 4.24, comma, 4.24. Now let's generalize. I want you to notice pattern. Half of math is being able to look at patterns and identify what's going on. And we see that to find my y coordinate, we did the radius times sine of the angle. To find the y coordinate number 2, we did the radius times the sine of the angle. And then to find my x coordinate, I did the radius times the cosine of the angle. And we did that in both problems. You can see it right there and right there. And so what we're going to do is we're going to generalize, and we're going to say that our x coordinate is equal to r times cosine of theta, and y equals r times sine of theta. Or if we wanted to write it in an ordered pair form, it's going to be r cosine theta is going to be the x coordinate, and r sine theta is going to be the y coordinate. So if you're given a polar point, you're trying to convert it to rectangular, just jump to this step right here. You don't have to draw your triangle and set up all the right triangle trig and solve every time. This is almost like a formula for telling you the horizontal component and the vertical component. On this video, we're going to go the other direction. If I start with an xy, can we convert that to an r theta? And this is also, I think, intuitive if you're strong with right triangle trigonometry. So if I go to the right 3 and up 4, here is that original point on A. And what we're trying to figure out is what is r and then what is theta. If I can figure out those two values, we'll be able to write our polar point. What we got to do here is we can see that if I drop a vertical and turn this into a triangle, we see this is a right triangle with one leg of 3 and one leg of 4. So I can use Pythagorean theorem to find my radius. We're just going to do the Pythagorean theorem, 3 squared plus 4 squared. And if you simplify that, you get the radius is 5. Now, how do we find theta? Once again, if we think about our right triangle, if I have a opposite of 4 and an adjacent of 3, we can use inverse trig to find the angle. So if I know tan theta, or tangent of our angle, equals opposite over adjacent, I can do tan inverse of opposite over adjacent, and that's going to spit out our angle. I can do that in the calculator. In this particular angle, our theta here is going to be about 53.13 degrees. So our point up here that we just wrote is we have an r of 5, and then I'll round that to about 53 degrees. That's that point. Now, let's do one more. If we can do one more point, we're going to learn some patterns that we can generalize. So our next one, it says -5, -6. So if I go to the left 5 and I go down 6, there is my point, okay? So here is my little right triangle. Now, if we're trying to find r, it doesn't really matter if I use the negatives or not, because we're going to square them. So I'm going to say that my radius is equal to 5 squared plus 6 squared, and that's going to be about 7.8 units. Now, in order to find our angle, we know that tan theta, if I want this angle right here, we can use right triangle trig to find that angle. And so we know that tan theta equals opposite over adjacent. I could put the negatives on it, but a negative over negative is going to be a positive anyways. So I do tan inverse of opposite over adjacent, and that's going to spit out my angles. And I got 50.19 degrees. Now we got to be a little bit careful. That's giving us our reference angle right here, okay? Due to the domain of tan inverse, it might not give us the angle that we're looking for. If this angle is 50.19 degrees, keep in mind in polar form, we're always measuring our angle off of that polar axis. So I need this full angle right here. So what I would want to do is I would want to take 180 and then add my 50.19 to it. And that's going to give me that our angle theta that we're looking for for this particular point is about 230.19 degrees. So if that's that, then our actual point could be written as 7.8, 230.19 degrees. Now, if we were to generalize this, what we see is this is going to be our general formula. If you're given a point in rectangular form, can you convert it to polar? So we could say that to find our radius, we're just going to do the Pythagorean theorem. To find our theta, we do tan inverse of opposite over adjacent. And that's kind of like your general formula. I think I have this summarized on my last slide, but my last slide is going to say convert from polar to rectangular. The x coordinate is r cosine theta and the y coordinate is r sine theta. And when you're converting from rectangular to polar, you're going to do Pythagorean theorem to find the radius and inverse tan to find your angle.